So in chapter 14, we learned that acids have a particular function. We learned that acids release H plus into solution, and we learned that bases release OH minus into solution. What we're going to do today is see what happens when we put these two into the same room and let them fight it out. But we got to get a couple definitions first. So we're going to talk about a couple of things. Acid-base models. We'll be discussing naming acids and bases. We'll be dealing with what happens when acids and bases react. And we're going to call that a neutralization reaction. You'll see why. And finally, we'll be looking at what we're going to call the acid/conjugate base system. So let's start with number one. What we're going to call acid-base models. And it's just a way of looking at what acids and bases do from a couple different perspectives. So the first one that we're going to look at is what we call the Arrhenius model. And this is the one that we're already familiar with. And we already know that acids release H plus. And so, according to this model, we'll slightly modify that definition. We'll say that acids increase the concentration of H plus, which is, of course, synonymous with H3O plus, and bases increase the concentration of OH minus. And that's a pretty solid model. We already know how that one works. Here's a different model that is saying the same thing, but from a slightly different perspective. We're going to call this the Bronsted-Lowry model. This guy's from Sweden, so he's got that funny looking O. According to the Bronsted-Lowry model, acids donate a proton. Now, before you start panicking, let's remember that H plus is a proton. Remember that a hydrogen atom has one proton and one electron and no neutrons. So if it has one proton and one electron, and then we yank it out of a water molecule, leaving the electron behind, what we're left with is one proton. And that's all an acid does, according to this model. Okay? The flip side of that model is what we're going to call what bases do, and that they accept a proton. In other words, if an acid donates an H plus, then a base is going to be something that accepts that proton. And it makes sense because if bases release OH minus into solution, there's really nothing more that they want to do with this OH minus than to hook up with an extra proton to make water. And we'll see that in a little bit when we get to what are called neutralization reactions. So these two models are saying the same thing, just from different perspectives. All right? Let's take a look at how we name acids and bases. Obviously, bases are really simple. We simply add hydroxide to the name. So we're not too really worried about that. Obviously, this is sodium hydroxide. Obviously, this is going to be barium hydroxide, and you get the idea how that works. But when it comes to naming acids, we're going to break naming acids up into two different categories. So when we are naming acids, we want to consider that there are two categories, what we're going to call binary acids and what we're going to call oxyacids. All right? Draw a line down here so we don't get them mixed up. Binary acids sound just like the name. It is an acid consisting of H plus and only one other element. So here's a couple of examples of binary acids. Remember, hydrogen and one other element. HF's a good example. HCl is a good example. H2S is a good example. And these, here's another one that's a good example. This is H3P is a good example. They have hydrogen and only one other element. And so that means that we're going to use what's called the hydro prefix to indicate that these are binary acids. So it works like this. If we have hydrogen and only one other element, such as fluorine, we're going to drop the ending and change it to ic. So this would give us hydrofluoric acid. Okay? If we were going to do the same thing with HCl, we're going to drop the chlorine and change it to ic. So this would give us hydrochloric. Notice that these all have this hydro prefix. Here's one, H2S. We're going to drop that ending and change it to ic. You can do it. Some people say hydrosulfic. Some people say hydrosulfuric. They both work. This would be obviously hydrophosphoric. So hopefully you're getting the hang of this. I don't know why that erased itself. Yeah, that's cool. All right, so when we have binary acids, they use the hydro prefix. What we call oxyacids, these are going to be acids that involve a polyatomic ion, and you should have that list of polyatomic ions on the back of your periodic table. And these are going to be any acids that contain H plus and a polyatomic ion. And polyatomic ions usually contain oxygen. Not always, but most of the time. And so we'll use this naming convention. We want to be careful because some of these polyatomic ions have formulas that are very similar, but slightly different. I'll give you an example here. We have two polyatomic ions from our polyatomic ions list. This is nitrate and nitrite. Be very careful because one ends in ate and one ends in ite. And what we're going to have to keep in mind is that they have slightly different naming conventions depending on how they end. It works like this, okay? First off, oxyacids don't use the hydro prefix, so we're not going to add that. But we are going to use this, and this is going to sound weird the first time that we see it. So you're going to hear me say this quite a lot. Oh, I see you ate. Did you save a bite for us? What do we mean by this? This sounds like a bunch of gibberish, Mr. O. You've lost it. It works like this. Anytime we have a polyatomic ion that ends in ATE, we're going to change that ending to IC. Anytime we have a polyatomic ion that ends in ITE, we're going to change it to US. So, of these two acids here, with nitrate and nitrite, if I was going to write the formulas, HNO3 would look like this. Well, it's a polyatomic ion that ends in 8. There is no hydro prefix, so we're going to drop off the nitrogen and change it to nitric acid. It ends in 8. Nitrite has the very similar formula, and the acid would look like this. They both have a charge of -1. So it ends in ITE. We're going to drop that nitrogen to nitrous acid. Okay? So be careful. That takes a little bit of practicing. All right, let's move on to what happens when these things interact. All right, let's take a look at what happens when we put acids and bases into the same reaction. We know according to the Arrhenius model, right? We saw that right up there at the top. I should spell it right. Arrhenius. That acids release H plus and bases release OH minus. You know this because you know HCl, when you put it in solution, dissociates into H plus and Cl minus, and you know that NaOH, when you put it in solution, dissociates into sodium and hydroxide. Well, what happens if we put them together? HCl and NaOH, and we know these are aqueous solutions. We know they both dissociate. Well, what's going to happen? Do you guys remember this? A double displacement reaction. And what happens when we react acids and bases in a double displacement reaction? We get BX and AY. Well, what's BX in this case? NaCl, your old buddy table salt, right? And what's AY? Check it out, ladies and gentlemen. A and Y. HOH. And if we were to write it like this, people are going to think that we're crazy. But if we write it like this, then it becomes way more familiar. This is called a neutralization reaction because an acid and a base went into the reaction, and when they came out, there is nothing left that resembles an acid or a base. And so their properties have been completely neutralized. So be careful when you're writing a neutralization reaction, because they should be balanced as much as possible. So if we were going to react, for example, say sulfuric acid with something like aluminum hydroxide, when we put them into solution, we know that the products are going to involve water and the remaining ions, aluminum with a charge of 3 plus and sulfate with a charge of 2 minus. So this is going to look like this. Incidentally, this is what we call, in a neutralization reaction, water and a salt. Not just table salt, but any compound with a positive and a negative ion is a salt. Okay, the last thing we're going to look at is what we're going to call conjugate acid-base pairs. Here's how this works. At the very beginning of chapter 14, we described that water sitting on the table would auto-ionize into H plus and OH minus. But we wrote it another way. We said that you could take two molecules of water, and what you'd get was called the hydronium ion and OH minus. And these two were two different ways of saying the same thing. By the same token, we could write that an acid in solution would dissociate into H plus and the remaining ion. But what we're not considering is that this has to take place in an aqueous setting. In other words, water has to be involved. And so there's another way to write this. Another way to write this would be to involve the water itself. And since water is pretty good at accepting another proton, we could write it like this. And this reaction is the same as the previous. It's just another way of writing it. However, according to the Bronsted-Lowry model, which we just saw up at the top, Bronsted-Lowry model, acids donate a proton. And that's cool because that's what this just did. It donated the proton to the H2O. Well, what does that make the H2O? According to the other half of the Bronsted-Lowry model, bases accept a proton, like this just did, to make H3O plus. And what that means is that this reaction looks different from which end of the reaction you're looking at. Does it run like this, where the HCl is the acid and the H2O is the base? Or does it run like this, where the H3O plus is the acid and the chloride is the base? Because if you look at it from the other perspective, H3O plus is going to donate a proton to Cl minus to make H2O and HCl. So it depends on the perspective. So what determines the direction a reaction runs is the strength. And what I have done here is I've put a list of acids, and notice that the increasing strength runs like this. It means that the acids listed at the top are the strongest: hydroiodic, perchloric, hydrobromic, hydrochloric, sulfuric. The ones listed near the bottom are the wimpiest. And notice that it also lists these as conjugate acids and conjugate bases. What does that mean? Well, let's take a reaction. Let's zoom in a bit. This guy right here is an acid called acetic acid. It's called vinegar, and it's a pretty common acid. And let's see what happens when we put this into a reaction and when we put this into water. So we're going to say acetic acid, it works like this. Here's that extra proton that it's going to donate, so don't panic. And in solution with water, what happens? Well, if it were to run in the forward direction, it would lose that proton and give it to water to make H3O plus, also called the hydronium ion. And that means that if it were to run in the forward direction, this is the acid and this is the base. But if we were to run it from the opposite direction, this would be the base. We're going to call this the conjugate base because it is the reverse of the acid. And we'll call this the conjugate acid. Well, which one is stronger? We have two acids involved, the acetic and the H3O plus called the hydronium ion. All we have to do is look on this chart for which of them is the stronger, which one is higher up, and look at this. The hydronium ion is a stronger acid than the acetic. And so if we were to put these two acids into the same reaction, the acetic acid just isn't strong enough, and the reaction has to run backwards. So it never actually dissociates to produce hydronium and the acetate ion, which is this guy. All right? It's called a conjugate acid-base pair, and all we're doing is comparing which is the stronger acid. All right? Take that for a spin, and I'll see you guys later.